What was that?
Good to go.
Wait, can you see my screen?
Yeah.
Yeah.
Okay. Yeah, so this is section 4.2, covering projections. This is a little bit of this is a review from Math 2415, but the projection on a vector, the projection of a vector onto another vector is another vector that's parallel. Okay, I should probably name these vectors. The projection onto vector B, or no, projection of vector B onto vector A is a vector that's parallel to A, but it's basically the shadow of B onto P. There's a few different things we need to know. There's the projection vector, which is given by this formula. There's the error vector, which is vector B, the one that's being projected, minus vector P, minus the projection vector. B plus E equals, no, so P plus E equals B, so E equals B minus P, where P is given by this formula. This is probably something you need to memorize. This is definitely something we need to memorize. It's going to be A dot B, so this vector times this vector, divided by A dot A, so this vector divided by itself, or dot with itself, and then times, and since this quotient is a scalar, we multiply that with the vector you're projecting onto, so A. And this is denoted proj B and with a subscript of A. The way I like to memorize this is that the A is a subscript and A dot A is in the denominator. And that helps me memorize the fact that A is in the denominator. This also works for projecting B onto a line that is parallel to A. So for example, if you have a line if you have this line right here, and you want to project this vector onto it, that's basically the same as projecting B onto A, since A is parallel to this line. If A and B are orthogonal, then the projection will be 0 because the dot product of A and B, right here, I'm not going to try and select it, but A dot B will equal 0, and so no matter what A is, the projection will be equal to 0. The projection vector will be the 0 vector. The projection matrix projection matrix P onto a vector A is a matrix that projects any vector onto A, which would mean multiplying matrix P B would be the same as projecting that would be the same as computing the vector projection of B onto A. Which is given by this formula right here, x. One second. Where did this x hat come from? Is that something I missed?
Yeah, maybe it's right there.
Okay. Yeah, this is something that confused me a lot. I think it's worth understanding. Okay, x hat is a scalar. X hat would be equal to B dot A over A dot A. So x hat would be this thing in parentheses. Over here. Okay. So the projection matrix onto A would be you'd simplify this product, I guess. You'd rearrange this using the commutative property of a scalar product, and you'd move this into the numerator and all that, and then you'd take this vector out of the numerator, and you get A transpose over A transpose A, A transpose A is just a dot I'm pretty sure that's just the dot product of A and A, and A transpose is actually a matrix, which is what is said right here actually. So if you have an n by if you have A as a vector in Rn, you'll end up with a projection matrix P being an n by n matrix. These are some of the most important formulas for projections. I think there's going to be more. I think there's more formulas too, especially when we get to least squares and all that. But these are some of the big ones so far. Any questions until now?
Yeah, 3. Isn't P just the projection formula? Or
Which one?
the third formula, could you clarify what that means?
Yeah, the projection vector is equal to the projection matrix times the vector you're projecting.
Oh, so you take the second formula above third formula, right? And then you multiply it by that B vector because that's the vector you're projecting onto, right?
Yes. So you're basically rearranging. You're combining formulas 1 and 2 and rearranging and simplifying.
Oh, I see. Makes sense. Thanks.
That works because the dot product is commutative. So you can actually rewrite this as A dot B, and you can write this scalar times A as A times this scalar. So you'd have A times vector A times a scalar with A dot B in the numerator, which is the same as A dot times vector B, and so on. Yeah. So here are some formulas that absolutely must be memorized. If you have an m by n matrix, the null space of A would be the null space of A transpose A. I'm not sure why that's important, but that's good to know, I guess. Okay, consequences of that are here. The rank of matrix A is equal to the rank of A transpose A. And the rank of matrix A is equal to the rank of A transpose. A transpose A could be a scalar depending on the dimensions of A. So if the columns of A are linearly independent, A transpose A is invertible because all of these statements are equivalent. Okay, this is projections onto a subspace. So if you have a subspace W and you have a vector B that is not necessarily in the subspace, the projection vector of B onto the subspace would be the vector closest to it. And this is basically what it looks like if W is a plane. So in other words, has a basis of 2, or if W's basis has dimension 2, the error vector will be orthogonal to W, the subspace. And we're using the definitions of orthogonality that we talked about yesterday, where a vector the error vector is orthogonal to W if and only if it's orthogonal to every vector in every basis of W. So here is how you find this least squared solution P. You want to set this equation up. Say A transpose A x equals A transpose B. So first of all, we set up AX equals B. If we assume there's no solution, we want to find the approximate least squared solution. We multiply both sides by A transpose. So A transpose A x or x hat equals A transpose B. And so x would equal the inverse of A transpose A times A transpose B. And so you get this as your solution to P for P. You get A times the inverse of A transpose A times A transpose times B, which can be a pretty ugly thing to compute. But your projection matrix will be A times A transpose A times the inverse of A transpose A times A transpose. So the error vector will be in the left null space of the subspace. Okay, so if we represent the subspace as the column space of some matrix, then the error vector would be in the left null space of the matrix. And so the vector B, which is the vector you're trying to find, the vector on the right hand side of the equation, the vector B will be expressed as some vector in the column space plus some vector in the left null space. Or no, it would be the sum of the projection of B onto the column space of A plus the projection of B onto the left null space of A. Yeah, this is way too dense for me to understand right now.
This is pretty dank.
I think there's another formula we need to memorize.
Which one?
It's the formula where it says P equals A times A transpose times A. You take the inverse of that product, and then yes, that one. I think we should probably memorize that one too. The projection matrix.
Yeah,
That guy.
probably. I think this
I'm
comes
gonna
up
make a
later
note
on.
on that.
Yeah, I think this comes up later on. I remember having to go back and look at this equation. I'm not sure what for, but I know this comes up. This is definitely something you need to know. I'm guessing this one too. Also, maybe even this. AX equals A times. Yeah. This should definitely be memorized. But now that I think about it, I think you can probably derive these two if you can memorize this. I don't know, if I were being safe, I would memorize all these. Okay. I think that's all the content. There's just a bunch of practice problems. Any questions?
So for I have the same notes as you, so I'm gonna look at page number for page 8. For that example, oh, she worked it out. To find the inverse of a 2 by 2 matrix, is it just 1 over AD minus BC, and then you switch AD,
Yep.
then you
Switch
negate the
AD
rest?
and negate these two. Yep.
So switch
You,
AD and then negate the rest, right?
yeah. Switch the ones on the main diagonal, negate the ones off the main diagonal for 2 by 2.
Gotcha. Only for 2 by 2.
Yeah.
All right, thanks for the review, man. I'll head out now.
See ya. Okay, yeah, let's do some problems. Problem 1. I think that's simple enough for a first problem. Let's take a few minutes to do problem 1. What was that?
Good to go. All right. I think we're good to go. Let me just run some tests really quick.
Yeah.
Can you guys like say test or something just so I can make sure that it's getting the sound on y'all's side?
I'm not sure if this is too much to ask, but shouldn't we go over Grant Schmidt, and because that's an application and I'm pretty sure that's going to be on the test.
Yeah, but that's like 4.4, isn't it?
Oh, I thought it was at this section. Never mind.
I think it's 4.4. Yeah, 4.4 is orthonormal bases and Gram-Schmidt. we ready? Let's go over it. So the projection vector P is equal to, well, since we're projecting B onto A dot A will be the numerator. So it would be A dot B over A dot A times vector A. And A dot B is equal to 5. And A dot A is equal to 1. Or sorry, 3. 3. And the vector A is equal to 1, 1, 1. So the answer would be 5/3, 5/3, 5/3. I didn't actually verify that E is perpendicular to A, but I'm pretty sure it should be. For part B, we're projecting B onto A, so we're using this formula: A dot B over A dot A times A. A dot B is equal to -11. A dot A is equal to 11. And vector A is -1, -3, -1. So simplifying this expression, we just get 1, 3, 1. I mean, this is equal to vector B. So the error vector will be the 0 vector. And I think it's trivially perpendicular to A because the dot product is equal to 0. Is that how it works?
For the error vector for that one, I got 0.
Yeah, 0 vector, right. I think it should be perpendicular to A, right? Because it's it's a 0 vector. It's 0 dot, the dot product of the 0 vector and anything else is the 0 vector is equal to 0, which should mean they're perpendicular.
It's kind of a weird one since it's like.
Yeah, definitely. Okay, any questions? Okay, let's move on to the harder ones. Let's do 5. Problem 5. Okay, should we go over it? Okay, I've sent an image containing my work. Okay. This is a pretty bad quality image, but okay, whatever. So the projection matrix onto vector A is onto vector A1 would be A1 transpose over A1 transpose A1, which would be equal to this vector times this vector, this matrix times this matrix divided by this vector dot product with itself, which would be this, which would be 1/5 times this thing, and similarly, same thing here. I think that's pretty straightforward. To multiply the two vectors, you get the zero matrix, and I wasn't able to come up with an explanation for why. Uh,
So I got like if E1 is equal to some scalar times A1 transpose, and then E2 is A2 A transpose, then when you multiply them together, you'll have to take the dot product of A1 and A2 to use the associated property.
uh, could you say it a little louder? I couldn't hear it.
Like when you multiply it together, it would be some scalar times A1 transpose A2 and then A2 transpose. So in the middle there would be A1 transpose A2, and then since A1 and A2 are orthogonal, then the whole thing would be
Oh, okay, yeah. A1 transpose. You're multiplying A1 transpose and A2. Uh, so that would be um, that wouldn't be the dot product of A1 and A2, would it? That would be the okay. A1 transpose times A2 would be um this this row vector times this column vector, and
take
multiply that out, you'll get the zero vector. Is that what it is? No, wait, that's not it. Oh no, okay.
So,
Yeah, go ahead.
so for some reason, something weird's going on where OBS can't like see your screen. Like everything's
Okay. Uh, okay. Was it working before?
uh I mean
Is this,
it with the other program I was using but not OBS. I don't know why.
oh, so all for all of today?
Say that again?
So was it working at all today?
Uh I mean ever since you pulled this up it stopped working.
Okay.
Like earlier when you were showing your screen, like with the
With the notes? Okay, is this better? Uh, Okay. Okay. Um. Okay. Okay. I can start numbering my. Yeah, I can start numbering the problems. That shouldn't be. That should make it easier. Okay. But I think I figured it out. It's because you're multiplying this times this times this times this, which is this times this times this times this, and in the middle you have these two multiplied by each other, which would give you uh, a 1 by 1 matrix, and the entry in the 1 by 1 matrix would be a 0. So you have a 3 by 1 times a 1 by 1 times a 3 by 1. But if the first one's a 0, which is basically a scalar, yeah, the 0 is a scalar. So you can pull that to the front, and you have this times 0, which is where the 0 comes from. If that makes sense. Yeah. Let's move on. I think there are a lot more harder problems. Uh, okay, let's do 11. Problem 11. What was that?
Good to go.
What was that?
Good to go.
Okay, I wasn't able to finish. I got most of part A. Um, what is P again? Lowercase p? The vector?
I think it's like the projection. The
The projection vector? Oh,
like the result.
no, that would be x hat. X hat is the result, because that's what we're trying to find, right? No, p, it says A times x hat is equal to p. So it would be the matrix 1 1 0 1 0 0 times x hat. Okay. Yeah, I'll need like 1 minute until and then I'll be done with part A. I'm just not going to do part B. Okay. I'll go over my solution part A. So this is uh my solution to 11A. Um, so the first thing you want to do is set up A transpose A uh, times x hat equals A transpose B. Um, I then found A transpose A times A. I multiplied both sides by its inverse. Then I computed the inverse. Then I multiplied everything through, and I found x hat to be negative 1, 3. And the projection vector P equals A times x hat, so it would be this matrix times this vector, which would be 2, 3, 0, which makes sense because that's the projection of this vector onto what looks to me like all of r squared. So it makes sense that it's just the same vector with just the z component cut off. And the error vector would be the vector b. So this vector 2, 3, 4 minus the projection vector, so it would be 0, 0, 4, which belongs to the orthogonal complement of the column space of A, because the column space of A looks like it's everything but the z components. And actually, what that would mean would be that multiplying that would mean the error vector would be part of the left null space. So multiplying this by A with this vector on the left would be that would be 0, 0, 4 times this matrix, which would give you the 0 vector, which means it's part of the left null space. And since the left null space and the column space are orthogonal complements, we conclude that this this vector is what is it asking? It's perpendicular to the columns of A. Any questions? Pretty straightforward, I'd say. I think it can get a lot more complicated though. Let's go on to like 13 maybe. No, not 13. Let's do 16. Yeah, let's do 16. Or actually, no, that's way too. It's way too similar. It's literally the same thing. It's ax equals b, except uh with no without much change.
Wait, so which one are we doing?
I haven't decided. It looks like they're all pretty similar to each other. Yeah, let's do 16. Call it a day. It's. I think it's a nice place to stop. Maybe we can do one more. Maybe we can do 4.3 afterwards. Or actually, do you want to do 4.3 now? Think it's not too late for that, or what?
Yeah, I think it would make sense because 4.3 is kind of similar, right?
What was that?
I was saying 4.3 is kind of similar, right?
Yeah, I'd say so. Let's do 4.3. Okay, this is 4.3. This section covers least squares approximation, which is when you have an inconsistent linear system. So in other words, a linear system that has no solutions, and you want to try to find an approximate solution, so a solution that's close enough. So in this case, you're finding So you have, let's say you have ax. Well, let's say um, let's say this plane is a column space of A, and this is your B. You want to find some vector, some linear combinations of the basis vectors of the column space of A, such that it adds up to B. But that's as you can see, it's impossible because B is outside of the plane. So what you want to do is you want to approximate it with the vector that's closest to the vector, but that's still inside the plane. And that vector turns out to be the projection vector. So this is called the normal system of equations. It's called A transpose A times x hat equals A transpose B, which is what we did in the last section. It's called the least squares error. Well, it's called the least squares solution because you're minimizing the error of this thing squared. So that's just the etymology of the least squares solution. One of the most wide-reaching applications of this would be linear regression, which is going to want to fit a line of best fit to a group of points even if this group of points doesn't actually belong on one line. And the way you do that is by taking the data points and you'd set those data points to be part of your matrix, I believe. Let's see. Okay, it's right here. The explanation's over here. So the model you use is y equals ct plus d. I don't know why they use t, but I guess that's just the convention right here. And then you set c and d as part of your unknowns, and so your unknown vector, so your x would contain c and d, and the um, the dependent variable will be part of uh, your solution variable, basically. So your b vector would be a vector containing your dependent variable, and your matrix would be your matrix would be the coefficients in front of these parameters. For example, d doesn't change. D is supposed to be a constant, and so the coefficient in front of d is 1. That's because your model is ct plus d. If it was ct plus I don't know, d d dt to the fourth, you'd compute t to the fourth, and that would be your coefficient in front of d. The benefit of that is that t to the fourth doesn't t to the fourth is something that you can compute, and it doesn't change the power on d. The system of equation is still linear with respect to c and d. And you solve this system of equations using least squares. A transpose A x hat equals A transpose B, and you solve this by multiplying both sides by the inverse of A transpose A and so on, and solving. This is an illustration of it. The actual data points would be these 3 points, and the line of best fit would be this line. The points on the data, the data points on the line would be these points with a box around them. And the least squared error would be the sum of the squares of these distances. I think that's what it is. I'm not sure actually.